In this video, we're going to continue our discussion of harmonic forcing. So in the last video, we were talking about the second order system expressed in terms of zeta and omega n with an input of a bar sine of omega t plus theta. So we have some sort of system and we provide some sort of force input to it, some sort of force or torque or something that causes this system to vibrate. And so we talked about how the solution x of t is going to be equal to some x steady state of t plus transient component x sub t. And it turns out that x steady state of t is going to equal some magnitude b times sine of omega times t plus theta plus some phi. So we'll notice a couple things here. First, so if the input is a sinusoid, then the output or the solution is in the steady state is also going to be a sinusoid. If we give the input some magnitude a bar, the output is going to have a different magnitude b. And if the input has a phase offset of I should say first, if the input has a frequency of capital omega, the output is going to have that same frequency, capital omega. And if the input is offset by some theta, then the output is going to be offset by some theta plus another offset phi. So it's going to be a sinusoid. The output is going to be a sinusoid with a different magnitude and a different offset, but the same frequency. And we can and we're going to introduce some equations here, which we'll be able to derive later in the course. But b, the magnitude b, is going to be equal to a bar divided by the square root, and we'll make that square root bigger, or it's the positive square root of omega n squared minus omega squared, and that whole quantity is squared, plus 2 zeta omega n times capital Omega squared. That quantity is squared, so this square root goes over the whole thing. And what we often do is we can factor that capital Omega out of the denominator there. And so this is going to equal some a bar divided by omega squared divided by the positive square root of omega n over capital Omega. That's squared minus 1 squared plus open quantity 2 zeta omega n over capital Omega, and that whole quantity is squared. Put the parentheses down there. Extend the square root. So it kind of looks like a Pythagorean theorem. You have the square root of two quantities that are squared there in the denominator, but that's the magnitude of b. This is the magnitude of the sinusoid that you get out, and you can see it's related to a lot of different things. It's related to the input frequency. It's related to the natural frequency and zeta. So the physical parameters omega n and zeta have an effect on the relative amplitude b to the input a bar. We'll also go ahead and introduce another equation that we'll be able to derive in a couple weeks ourselves. But phi is equal to a tan 2 of minus 2 zeta omega n times capital Omega, comma, omega n squared minus capital Omega squared. So if you'll remember, a tan 2 takes two inputs, y and x, and it's analogous to the arctangent, so just the regular atan of y over x, but when we give it the two inputs separately like this, we can maintain a negative sign if there is one. So atan 2 allows us to get an answer phi anywhere from 0 to 360 degrees, 0 to 2 pi, whereas atan is always going to give an answer between negative pi over 2 and pi over 2. So atan 2 gives us more information. We can rewrite this as we'll factor out the that omega again. And so we've got minus 2 zeta omega n. Oh, sorry. Gonna back up there. Minus 2 zeta times capital omega over omega n, comma, 1 minus omega over omega n squared. And in both of these cases, for both the phi and the b, when we factor out that omega, the capital omega, we end up, rather than having omega n and omega separately, everywhere we see the ratio of capital omega to omega n, which is the natural frequency. And so that's why we factored these things out.